If I ask you to picture an electron, you probably think of a tiny charged particle whizzing around the nucleus of an atom, much like planets orbit around the sun. And in chemistry, we're taught how the filling of these orbitals determines elements' chemical properties, giving rise to the trends that we see in the periodic table. In a large collection of atoms, like in a bulk solid, the electronic behavior determines very important material properties, like electrical conductivity and optical responsivity. That is, how do the electrons move in the material, and how does the material respond in the presence of light? But it's not until we take a closer look at electrons that we realize they behave more like clouds of probability, changing the way we think about their position and velocity. And aside from being extremely small, electrons also move exceptionally fast, with changes to the probability cloud taking place on the order of attoseconds. That's 10 to the minus 18 seconds. To put that into perspective, there are more attoseconds in 1 second than there are seconds in the age of the universe. My PhD thesis investigates how we can observe and control electron motion with the use of ultra-short pulses of high-intensity light from lasers. We can use this light to observe how the electron motion moves and behaves in these really short timescales with a few different techniques that allow us to kind of compare this to the way that a fast shutter speed camera can capture a fast-moving object. So in the same way we can see dynamic movement in a horse's gallop, we can see dynamic movement in the electron cloud. This allows us to do this with a technique called pump probe, which uses one light pulse to excite a system of electrons and a second light pulse to kick out those electrons, the probe, so that we can measure their energy and momentum. From the time delay between the pump and the probe, we can see how the system evolves in time, giving us a glimpse of how the electrons behave at any given moment in time. We can do this by generating light sources over the entire electromagnetic spectrum, from the long wave infrared to the extreme ultraviolet. It's not only important to learn about these kinds of processes from a fundamental science perspective, it's also important to do this so that we can learn how to control the precise products of chemical reactions and drive high-speed electronic devices. Just this year, the Nobel Prize in Physics was awarded to the developers of laser technology that paved the way for this research to be able to happen in the first place, as well as its applications to medicine and industry. It is thus really important for us to learn how to further develop our understanding of light-matter interaction so that we can keep pushing the boundaries of current and emerging technology into new and exciting territory. Thank you.